Good morning, good afternoon, and good evening to everyone. Welcome to this Frontiers Forum deep dive session on a digital twin of Earth's water cycle, progress and promise. My name is Gilbert de Gregorio. I'm the Associate Director of the Frontiers Planet Prize, and I will be your host over the next 90 minutes, and I'm really excited to be chairing this fantastic session today. And a brief introduction to Frontiers in Science. This is our flagship multidisciplinary open access journal that focuses on the transformational science that is needed to accelerate solutions to enable healthy lives on a healthy planet. The journal publishes invited, peer-reviewed lead articles within a hub of multi-audience content designed to extend their reach across science, policy, and the general public. Today's deep dive focuses on the Frontiers in Science lead article by the researcher Brocca and his co-authors, and is entitled A Digital Twin of the Terrestrial Water Cycle, a glimpse into the future through high-resolution Earth observations, which was published in March this year. The article describes the digital twin Earth hydrology platform, which was built by the European Space Agency, a groundbreaking step towards a virtual replica of the terrestrial water cycle, which combines new high-resolution satellite observations and cutting-edge modeling to build a test environment for our platform. The authors discuss how it was created, as well as its practical applications, and presents a roadmap for expanding their demonstration models from 4 case studies in the Mediterranean basin to a continental and at a global scale. And this is the article hub, which includes an editorial by Professor Anna Barros from the University of Illinois, viewpoint articles by Professor Bob Su and Dr. Yizhan Zheng from the University of Twente, and Professor Christina Naomi Tag from the University of California in Santa Barbara. We also have a policy outlook by Dr. Giriraj Amarnath of the International Water Management Institute, who is joining us today on our panel discussion. There is also a lay explainer, infographics, a video, even an article within the journal Frontiers for Young Minds, which is our journal for kids. And in this deep dive session, you'll hear from many of the contributors to this article hub, and you'll also have your chance and opportunity to ask them questions directly today. So let's get started. And this is the agenda we have over the next 90 minutes. Firstly, we will be hearing from the authors, Dr. Luca Brocca from the Italian National Research Council. He will be introducing the digital twin Earth of the terrestrial water cycle and will be setting the scene for today's discussions. He will then be followed by Dr. Lorenzo Alfieri from the CIMA Research Foundation in Italy, who will be discussing high-resolution satellite products for hydrological modeling, and Dr. Mariette Vreugdenhil from the Vienna University of Technology, who will be exploring the technical challenges of Earth observation. And then we'll move on to a panel discussion and a live Q&A session with 2 guest panelists joining our speakers. And they will be Dr. Giriraj Amarnath from the International Water Management Institute and Professor Ilias Pechlivanidis from the Swedish Meteorological and Hydrological Institute. So let's get started. And I would like to turn to our first speaker, Dr. Luca Brocca. So a few words about Luca. He is a director of research at the Italian National Research Council, the Research Institute for Geo-Hydrological Protection in Perugia. Luca develops innovative methods for exploiting satellite observations in hydrological applications, such as floods, landslides, drought, and agriculture. And he is a prolific author, co-authored over 160 journal articles, and has actively participated as a principal investigator and co-PI in several European research projects, and has been cited over 10,000 times. So without further ado, Luca, a warm welcome, and I'd like to hand over to you.
Thank you very much, Gilbert. In these first introductory slides, I will talk you about this article that is basically based on an activity that we are running in the last 3 years with 11 international institutions altogether. And I'm just basically coordinating the activities of many a very good team. And the topic is to develop a digital twin of the terrestrial water cycle. Let's start from why. I guess that everybody knows about the storm Daniel that occurred in southeastern Europe, in Greece in particular, and in Northern Africa last September 2023. And it's very huge. For instance, the amount of water that the area that is flooded in Greece, that is more than close to 1,000 square kilometer. And it was simply called like a Noah floods. And you can see actually, if you look at the image, basically you see the hill that looks like a highland in the sea. But the worst situation was in the northern Italy, in northern Africa, where in Libya, the number of casualties was more than 10,000. And still, the number still has to be confirmed. And this is for a single flood event occurred last year, but the floods are occurring more and more. And I have another example, for instance, in Italy. Next slide. There is some shift, so sorry, but on a few months before in Italy, we have two storm events occurred exactly on the same area at the beginning of May and at the end of the May. And in a time slide of 15 days, we have two events with more than 200 millimeters in 36 hours. And of course, we had a lot of flooding, and for instance, the flooded area lasted for more than 15 days. And since when I started to do this job, this never happened in Italy. And what is the reason for these kind of things? Actually, I'm not meteorologist, but colleagues from meteorology, because actually also in Greece, the same happens 15 days later of the storm events of the storm Daniel. Another very strong storm events occurred in the same area. And this is due to the change in the atmospheric circulation and to the very high sea temperature that we have in the Mediterranean. These two factors means that we will have more and more events like this. And this is, of course, strongly related to global warming and climate changing. So we have to address these problems, and this is not the problem of this is not only a problem of flooding, but also of other extreme events, and also water resource management. So that's why we started these activities called Digital Twin Health Hydrology. That basically the idea is to develop the shift is really. Okay, this is the slide for introduction. Basically, what is a digital twin Earth? What was the digital twin Earth hydrology project? It's a project of 2 years with the budget around 2 million euros with also ancillary projects. And the idea is to develop and demonstrate a prototype of digital twin with a focus on the terrestrial water cycle. I will give you some example later. And the first area that we focus on was the Mediterranean basin. And what we developed, what are the main new activity that we develop in this project are the high resolution meteorological observation. This is the example for precipitation. During the project, my colleagues were able to develop high resolution precipitation from space, which means 1 kilometer, 1 hour. In the animation, you can see precipitation for a few days in the Po River basin, and that is in northern Italy. And this product is high resolution in time and space, and we found also it outperforms other events. And this kind of resolution is needed if you want to address flood and landslide events that typically occur at very high resolution. Similarly, we have for San Mosto, this is a very nice example, but I have a lot of them. Actually, we have published the dataset that are freely available in the platform, that you can access to the platform in going to the link that you can see in the slide in the bottom left, but also in the QR code. But in the slide here, you can see in the middle the map of Sentinel-1 San Mosto, and you can easily see that the area that are wetter, bluish colors, are exactly the same area for which we have the occurrence of precipitation. And here we have precipitation obtained from radar, and you can easily see how close the pattern are between San Mosto and precipitation. And so basically this San Mosto product is able to actually to detect at high resolution the footprint of precipitation over the ground. Another very nice data sets that we developed in this project, but also in other ESA, and not only ESA is not only from European Space Agency, but also project from the European Commission, was for the first time to provide the high resolution irrigation water use from space. Irrigation is the major water consumer in the Mediterranean area in many basins. It's without the knowledge of irrigation, actually, we are not able to simulate the terrestrial water cycle. And again, by using Sentinel observation, and not only, we were able to obtain high resolution irrigation water use. We have example now for 4 river basin in northern Italy, Spain, France, and also in Tunisia. But now the target is to develop datasets for the whole Europe and Northern Africa. So we have these high resolution datasets. And what we have done? We have done for the full Mediterranean, this video actually very nicely shows basically the final output of the project. We developed this high resolution precipitation data that is what is new with respect to the past. Of course, we have already precipitation and soil moisture and evaporation data from space. But since a few years ago, these products are available with either coarse resolution, 20 kilometer, or 10 or 20 kilometer, either coarse resolution in time, like we had, I don't know, monthly resolution. But now with the advent of Sentinel and other techniques, we were able to develop a high resolution precipitation and soil moisture and other. So we have this high resolution data ready. And we have used this data together with advanced hydrological modeling. And for instance, we were able to simulate high resolution flooding. What we did, for instance, in the project, and you can see in the platform that I will show you later, the simulation of the flooding events that occurred in Sicily at the end of 2022. October 2021, you can see here flooding events. You see flooded area, but also flood speed at 5-meter resolution. And basically, these data are obtained by integration of high resolution precipitation and modeling. And the idea of the project is not only to develop simulation data, but also to develop what we call what-if scenario. What-if scenario means, this is the example for flooding, means that if you know the two most important variables, for instance, for simulating flooding, that are soil moisture and precipitation, I will have an example also later. You can provide different scenarios. These are scenarios for the Po River Basin, but in principle, you can do for the whole Mediterranean Basin. And in the next activities, we are going to make it very likely for the whole Europe and not only, also in Africa. And this scenario can be very useful for stakeholders, for scientists, for citizens, to address the problem that, for instance, are shown here in the slide with the drought and flood events that occurred just in the last few years. And actually, this animation is not considering the flooding occurred in 2023 and 2024 now. So what is the main output? The main output, the more tangible output of the project is the DTE hydrology platform that is open access. You can have access to this by clicking on the QR code. And what is shown here in the animation is the what-if scenario for flood risk assessment. And for instance, and I will give you an example, what are the two main variables that we need to know for simulating floods? Initial soil moisture and precipitation. If you go in the platform, you can easily try to simulate flooding for the Po River Basin. This is just a prototype, just an example for a few points of the basin. But actually, the idea is that basically you can do it for everywhere. Just try to make it an example. We don't have too much time today, but so in principle, we can do this interactively, but I will not do it today. But for instance, if I have initial condition of 0.3 means 30% and precipitation of 140 millimeter, we have a peak discharge of close to 4,400 cubic meters per second. So the question could be, if we increase initial soil moisture to 70%, what will be the peak of river discharge? And in the platform, you can easily answer this question. And in principle, I wanted to make this question to everybody to see how much we are close to all the people that now are joining the meeting, because it will be a very nice exercise. But we will do it probably later, or not later, in another day. But so, for instance, in the platform, you can quickly access to this, and you put 0.7 here in the box. I don't know if you see my pointer, but in the box on the top right. And you can easily see that if we increase from 30 to 70% without considering an increase in precipitation, we will have an increase of peak discharge up to 7,000 square kilometer, 7,000 square meter per second, which means that we touch the red line, which means that the Po River Basin is going to flooding. And this is very important for stakeholders involved in flood prediction, but and is very easy to use also for citizens and for everybody who wants to understand how much can be important the precipitation events in different basins. The same we did for the water resource management. Here the problem is a bit more complex because it's not only precipitation and soil moisture, but the important is also the snow, the high temperature, and also in principle here in the Po River Basin, the level of the water reservoir. But again, in the platform, there is a cursor on the top, on the bottom left. You can play with them, and you can have access to what could be, for instance, in the next summer, the water use for the Po River Basin. I don't have example here, again, for the question of time, but you can easily see if we, for instance, in a particular condition like we had in 2022, probably you know that we had the worst drought in the northern Italy in the last 100 years. And with the platform, you can easily understand what can be the deficit in water use, and so what can be the loss of water for irrigation. And so probably you can also manage irrigation differently. And this is actually what was done in northern Italy to address the problem. But the platform provides you easy example to answer to this question. Now, it seems that we made a lot of stuff, and this is true. But actually, the challenge is that still we have to address are really a lot. And in principle, I can tell you that on my side, I think that we are at the very beginning, because the terrestrial water cycle is a very complex problem. And here are the 5 challenges that I wanted to underline, but probably there could be something else. And one of them is the spatial resolution of the data and of the modeling. Typically, we see high resolution data that are not really high resolution. And the same for the modeling. Then when we integrate a lot of modeling and data, we should take care about the consistency and the independency of the data. Sometimes we integrate data that already came from modeling, so that's a problem itself. There is a lot of complexity in the terrestrial water cycle that should be addressed. I have mentioned the human processes like irrigation, water management, but also physical processes at high resolution. Finally, how to make the modeling. This is a very important question. It's not really true, but there could be 2 different ways, like doing a modular approach in which many people can contribute, or a centralized approach that can be very strong, but probably it will lose the opportunity to make the whole community to collaborate. And finally, once we have to address the problem of managing big data, we have to take care a lot on how we develop data infrastructure and also the front-end visualization and this kind of things. Let me give you some example. Just a couple. This is on left, precipitation for an event that occurred again in northern Italy. It was not clear, I came from Italy. And on the right, you can see different soil moisture maps before and after precipitation. All the products except the ones on the bottom right should be high resolution, which means 1 kilometer. But if you simply see the maps before and after, you can easily see that, for instance, the two top figure from Central 1 are really high resolution, but the same cannot be said for the 2 picture in the middle, and also the ones in the bottom left, it can be managed. So basically, we have to take care a lot on when we take the data, what is the real resolution, the actual resolution of the data. A similar problem is the consistency of the product. This is just a very complex slide that I don't want to provide you a lot of example, but for instance, in our project, Digital Twin Hydrology and 4D Hydrology project, we develop different data sets for precipitation, for vegetation of depth, for radiation, for evaporation, and blah, blah, blah. But then we developed also modeling, and we developed complex product for instance, for interception, for snow melt, runoff, terrestrial water storage. And if you look at the arrows, basically they tell us the dependency between the different products. And so we have to really be aware of this dependency, because if we want to use some of the products in some modeling or all the products together, we have to take care about that. Most of the time we use the data because actually we are expert in a different domain, and we use the data without taking care about that. Another problem is the modular approach. Just to give you an example for flooding, here you can see in the different boxes, each of them is a product that we get, for instance, from satellite. The symbol is not really properly working, but should be a satellite. But in any case, all the boxes with the picture, no, it's okay. It looks a satellite, very stylized. And each of them is developed by a team working on developing of satellite products. So for example, for surface most, we have people from Wien, from University of Vienna in Austria. For precipitation, our group. For evaporation, people in Belgium. For snow, people in northern Italy. For CIMA. And so that's the problem. Each of the products is used together with modeling, and the modeling are composed of different modules. And so, for instance, we have a model for snow melt, we have a model for the soil water balance, a model for groundwater, for routing, many things. And you can see that also this slide is very complex, and it is just to address the flood risk target, with many different interaction between people working with satellite data, people for modeling, and at the end, also people for the visualization of the data and for the use of the data. So basically, it needs really a community effort, and the modular approach for that is really the way to go, even though it is more complex because it needs the involvement and the collaboration of many people together. Let's go to my final slides, if it runs. I want to underline what we have done in this paper, in this article, because it's not only the article as mentioned by Gilbert before, but we have also an article for the young people. This was one of the best experience in writing a paper in my career, and I've written a bit of papers, so that's really nice. And if you are out of the field, reading this paper is really an easy way to start this the understanding of what we have done. And this was written very well because it's written actually by me, but by one of the Frontiers editor, and it's a very nice piece of work. Let's go to my final slides. On the left, you can see the article. On the right, again, the animation that is working a bit low in this for today because probably we have many people connected. And you can see in the slide my contacts. For any questions, you can ask me also later, and not only during this 1 hour and a half that I think will run very fast. And thank you very much for your understanding, for your listening.
Thank you very much, Luca. It was great setting the scene and sharing such a powerful platform. I'm sure that everyone watching this is flocking now to use the DTE hydrology platform and testing this out themselves, despite all the challenges that you've seen. I would like to move to our next speaker, Dr. Lorenzo Alfieri. So welcome, Lorenzo. Lorenzo is a researcher at the CIMA Research Foundation in Italy and is a specialist in flood modeling and disaster risk management. Lorenzo is one of the main developers of the European and global flood early warning systems, which are currently operational through the Copernicus Earth Observation Programme of the European Union. His current research focuses on natural hazards, flood mapping, assessment of flood risk in the present and future climates, climate change adaptation, riverine, and flash flood forecasting. So without further ado, Lorenzo, I hand over to you. The floor is yours.
Thank you very much, Gilbert. And it's a pleasure to be here. Today, I'm going to give you some insight from hydrological modeler perspective on the use of these high-resolution satellite products that were developed in the context of the Digital Twin Earth hydrology project. With this project, we wanted to develop and demonstrate the prototype of a digital twin Earth with a focus on the water cycle and hydrological processes, especially focusing on their impacts due to flooding. I had the pleasure to work with Luca and also with other European partners in the development of this work, and to hopefully to advance science in the theme of digital twins. So moving to next slide. I wanted to start, I wanted to focus on the Po River Basin, which is in the northern Italy, because that is where we started this fruitful collaboration on the digital twins. And in fact, it's where we run most of our research experiments that then gave us the opportunity to run this on a wider scale, at the European scale. So the Po River Basin is about 74,000 square kilometers in the northern Italy. It's the largest Italian basin. And it includes a good amount of the Italian population, agricultural production, and zootechnical production. But also, it's probably one of the best monitored river basins in the world, because we have a very dense network of in situ data, of meteorological observation data, including rain gauges, temperature, relative humidity, wind speed, solar radiation, and snow gauges. We also have efficient network of weather radars, where we can estimate spatial maps with high spatial and temporal resolution of precipitation. And so we could model this basin from the hydrological point of view with a very high resolution. So one might wonder, why do we want to use satellite data here? Well, that's exactly the point. So we want to see if state-of-the-art satellite data can beat the performance of an hydrological model run with very high resolution data. In this case, as you can see, we had also the massive presence of dams. We modeled 99 dams in the system, and the 3 major lakes, which are among the biggest lakes in Italy. We ran this at 1 kilometer resolution and 1 hour temporally. And we did a number of experiments by forcing the model with satellite data. So going to next slide, we used the continuum hydrological model, which was developed at CIMA Foundation over the past 20 years. It's a fully distributed, physically based hydrological model. What does it mean? It means that the territory, in this case, the Po River Basin, was modeled through a regular grid of 1 by 1 kilometer resolution. And for each grid, we simulate all the hydrological processes occurring. The model is freely available on the GitHub page. We have a number of dynamic input, which is typically the meteorological data. And then we also have static data, which include the digital elevation, soil characteristic, vegetation, and so on. And also we have a number of parameters that can be fine-tuned through model calibration. The main output that we look at is discharge, so moisture, land surface temperature, evapotranspiration, but basically we can model and take out all the main hydrological variables. Next slide, please. And here we start with the satellite product that we tested within this experiment. Basically, thanks to the collaboration with different European partners, we had at our disposal a number of satellite-based products that can be used as input in the model. This type of product do not enter in the same way, all in the same way in the hydrological model. In fact, we tested high resolution precipitation data from SM terrain, and also the GLIM evapotranspiration data set from University of Ghent as a forcing input. Then we also tested the influence of RT1 soil moisture data and sea snow depth as data simulation. And finally, we used satellite-derived estimate of discharges as a benchmark data for model calibration. So quite a variety of ways through which this satellite data can interact and benefit the hydrological model. Next slide, please. Okay, so we run a baseline run, what I mentioned before, that is fully run on in situ data, so high resolution data. We got relatively high performance variable throughout the basin. We focus on the period 2017 to 2019, running at high resolution. We had about 20 discharge stations that were used in the calibration, and also 5 independent stations that were used only in validation and with a different period. So we can say that these were for a good amount completely dependent on the other basins. We also noted that performance generally increased for higher basin area, meaning for stations which are more downstream, where the errors basically tend to like even out and get better for performance. Next slide, please. Okay, so here the results that we obtained at the different stations by running the various experiments. We basically run one experiment for each of the 4 products that I mentioned, plus one experiment with all the data, all the satellite product together. What we found is a scale for extraction of river discharge for all the experiments. So in all cases, we found almost complete like scale above the no scale line in terms of clean group efficiency. That was found at the 27 station between 0.13 and 0.53. Interesting to see is that despite the very high quality of the in situ data, simulations including satellite-derived snow depth and satellite-derived evapotranspiration performed slightly better than the baseline run, with mean improvement of about 4% and 2% respectively. And also very interesting is that the simulation were around with all the Earth observation products showed a slight deterioration in the mean performance in the calibration, but very good skills in the validation at the validation station. So those that did not depend strongly on the calibration stuff. Next slide, please. Here, for example, you see the output at two validation stations. Sorry, so stations that were not specifically calibrated, the Toccia at Candolia and the Po in Piacenza, and you can see that especially in around the peaks, we got very good performance in terms of reproducing river discharges for these 2 events. In particular, the one occurred in October, between October and December 2019 in the main reach of the Po River, caused a flooding around the city of Piacenza, basically north of Piacenza. And we can see that in this case, even the simulation fully run on Earth observation data, so from satellite data, provided very good skill that would have been able to reproduce this flooding in high resolution. Next slide, please. So where do we want to go next? Of course, this is a research experiment, but we don't want to stop here. We want to go, especially at CIMA Foundation, to operational system. And we are already implemented this knowledge to develop impact-based flood forecasting system on larger areas, in this case in East Africa, at very high resolution, both spatial and temporal, so typically around 1 kilometer and 1 hour resolution. In this way, we are able to model fine-scale processes, not only spatially, but also temporally, because we know that in areas with significant presence of convection, sub-daily events are very important and very destructive, meaning flash flood and urban flooding. So in this case, we used again the continuum distributed hydrological model and link it to threshold exceedance analysis to to forecast potential discharge event with a high magnitude, so potentially linked to flooding condition. And then we linked this input to inundation mapping, and on which we perform impact assessment applied to 5-day forecast and 6 exposure layers, to plus also estimating flood warning levels based on impacts. This is a paper we just published. Next slide, please. Okay, here also some related research that we recently published. In this case, again, related to the Po River Basin. What we found, that I want to stress as outcome of this work, is the importance of integrating geophysical modeling, such as hydrological modeling, with in situ data and also satellite data to improve high resolution monitoring and forecasting of hydrological variables. So it doesn't mean that we have to use only satellite data when other type of data is available, but the best solution is probably optimal integration of this type of data. In another paper, which focused more on the severe drought that was observed in the Po Basin in the last 2 years, we also found the importance of including the human influence on the water cycles, such as dams, reservoir, irrigation, flood barriers, to improve the characterization of the hydrological processes and of river discharges. So, of course, the human influence is important, and even more when in times of severe drought. So this is very important to include it also in the hydrological modeling. And with this, I think I've concluded. So let's go to the next slide, and over to Gilbert now. Thank you very much.
Thank you very much, Lorenzo. That was really, really engaging. And to finalize our speaker lineup, I'm pleased to introduce Dr. Mariette Vreugdenhil, a senior scientist at TU Vienna, the Vienna University of Technology. And Mariette is a remote sensing expert. She has a background in earth sciences, working on Earth observation data for applications such as drought monitoring. And her research focuses on improving our understanding of land surface processes in changing climates and mitigating risks related to natural disasters. So to close off our keynotes, Mariette, a very warm welcome to you, and the floor is yours.
Thank you, Gilbert. Yeah, so I will be talking about how we actually built the high-resolution Earth observation data cube, so the data that was used in the modeling that was shown before by Lorenzo and Luca. So in the project, focused on developing Earth observation data sets that can be used for hydrology. So if we think about the scales in hydrology and the information that we need, there have been already a lot of studies, especially like in the 80s and 90s by my PhD supervisor, Günter Blöschel. And we have different scales in hydrology and different scales where the processes are taking place. And in terms of Earth observation, where we used to be in the scales that we could actually observe with satellites was the dark blue area. So we either had, let's say, a high temporal resolution, but a very coarse spatial resolution, like a 10 to 20 of kilometers, or we would have a very high spatial resolution, but let's say maybe like monthly to yearly observations. And in the era of the Copernicus satellites by ESA, we can now go towards a high spatial and temporal resolution. So this is also where we want to go with the digital twins to get closer to observing these hydrological processes that are so important, such as storm flows. So let's say the variables that we've been working with in this project, and also for this digital twin that you saw also in the previous slides, are, let's say, the highly variable hydrological processes. So for this, we need precipitation, snow water equivalent, soil moisture, and evaporation. And this is also what is available through the DTE platform. And in order to do flood forecasting, we need high resolution, which means sub-daily observations, and preferably 1 kilometer resolution, or even better, of course. So yeah, we've done this over with the study area of the Po Valley, which you've already seen before. And we encountered while we were, let's say, retrieving these variables from Earth observation data, we've used, let's say, a suite of satellites, and we've encountered quite some challenges. I'm sorry, I'm waiting for the slide to go forward. Which, yes. Sorry. Yeah, so what we did is we combined, so as I said before, we combined a suite of Earth observation data sets and satellites. So you see here on the right, let's say the Earth observation missions from ESA. And we actually combined data from the science missions, the Copernicus missions, but also from EUMETSAT's and ESA's meteorology missions. And the advantage of, let's say, the Copernicus and the meteorology missions of EUMETSAT is that they are very consistent, and they have, let's say, planned launches for new satellites until in the future. So, for example, we work with METOP ASCAT, which is a satellite that was actually designed for monitoring wind speeds over oceans. And there is like the second generation of satellites and launches is planned until 2040. So this means that what we've been developing now with the satellite data sets that we've been using now, we can also use in the future. So it is not that when one of the satellites is decommissioned that there's no Earth observation data anymore for this digital twin, but we're using satellites that are already planned for, let's say, the coming decades. So some of the challenges that we have encountered during our retrieval of then, let's say, the variables precipitation, snow water equivalent, soil moisture, and evaporation are although we have our new satellites, so we use the Copernicus satellites, which provide us with a high temporal and spatial resolution, the temporal resolution still leaves something to wish for. So, for example, for Sentinel-1, we have a observation interval of, let's say, 1 to 3 days at best, and currently with only one Sentinel satellite in orbit, it's actually more going towards, let's say, 2 to 6 days. So for the very high resolution satellites, we still have a relatively low temporal revisit time, but then there's also other factors that are affecting our Earth observation. So, for example, cloud cover will affect any optical satellite data sets, as it doesn't penetrate the cloud, so we can't observe vegetation during cloud cover. Also, dense vegetation is a challenge. For example, if we want to retrieve soil moisture, if we have a very dense forest, the signal doesn't penetrate into the soil. So here it's impossible almost to retrieve soil moisture. So for example, over tropical forests, there will be data caps because it's not possible to do any retrievals. And then we also have, let's say, confounding variables, which leads to data gaps in the one or the other data set. So an example is for Sentinel-1, we use backscatter data in the microwave domain. And in winter, this is sensitive to snow cover. So snow water equivalent can also be retrieved from Sentinel-1 backscatter observations. It is also used for soil moisture observations. So you can imagine that as soon as there's snow cover, we cannot retrieve soil moisture anymore. So this also leads to data gaps. And of course, for modeling, what is needed is usually, let's say, a very homogeneous data set. But with Earth observation, this is really a challenge still. Then the other things that we encountered is the heterogeneity of the landscape. So retrieval models, as they were for, let's say, coarse resolution satellites, they could make assumptions that made the models much easier. If we observe an area of 20 by 20 kilometers, we can assume that, let's say, the landscape is very heterogeneous, so we don't need to take into account, for example, vegetation structure, because it's impossible. So we assume these are static, let's say, or soil surface roughness over very large areas. We assume soil surface roughness is a static variable. But of course, if we're going towards the kilometer scale, we can observe individual fields and forests where you can imagine that roughness of the soils, if one farmer has plowed their field and the other hasn't, the soil surface roughness will be very different. And this will affect also our retrievals of soil moisture. And these were things that we needed to take into account when we went from, let's say, a 25 kilometer pixel to a 1 kilometer pixel. And then one of the challenges that we have also encountered is the validation data that is lacking at the 1 kilometer scale. So the picture you see here is of a validation campaign in Australia with my colleague Delphine Leroux, who's also joining this presentation, I think. So it needs, we need validation data to actually look at if our retrievals are correct. And we can do this using in situ data sets, but usually in situ data sets only have 1 point measurement for a very large area. And so still, there are no in situ data sets really tailored towards validating and calibrating, let's say, high resolution Earth observation data sets. So to give you a short introduction to, let's say, the advances that we made within the DT hydrology project. So if we look at the soil moisture from Sentinel-1, I told you we used backscatter data, so VV polarized backscatter data. And what we did is that so for the project, we worked at a 1 kilometer scale. And what we did is we used the 20-meter sampling that we have from Sentinel-1 VV backscatter to improve the pre-processing. So what we did is, for example, at 20 meters, we took out those pixels that were insensitive to soil moisture. So you see an example here for Spain, where in some areas we found that the signal was very sensitive to, let's say, rocks that were in the subsurface of the soil and in the topsoil. And for these pixels, we took them out at the 20-meter scale, and then we resampled to, let's say, the 500-meter sampling that we use for DT hydrology, which means a 1 kilometer resolution. And then we only use the pixels where we knew that we are able to retrieve soil moisture. And the same we did for dense vegetation. So for very dense vegetation, we take the pixels out at 20 meters and then we resample to 500 meters. We also started to use high resolution dynamic vegetation parameterization because what I said, at this high resolution, we need to better capture the vegetation dynamics in order to retrieve the soil moisture, because the backscatter signal is sensitive to soil moisture and vegetation. And if we continue then to an example, or let's say we look at the validation of this. So what we're seeing here is that then we compared our Earth observation retrievals actually with a model. So this is AR5 land at 9 kilometers. So we're looking at very different spatial scales, but this is currently the best reference model that we have. And we can see that we have a very high correlation over many regions. So this is for the full Mediterranean region. But if we look at the Po Valley, we can see very high correlations. But also we see that at, for example, high elevated areas in the northern region, we can see some lower correlations due to data gaps, due to, let's say, denser vegetation, due to snow cover, but also due to the terrain, which is more complex. And next we go quickly into the evaporation retrievals. So the evaporation retrieval was done by the University of Ghent. So Diego Miralles and Dominic Rijns, their groups. And what they did is they combined for the evaporation retrieval, they combined 2 satellites. So what they did is that they combined Sentinel-3 land surface temperature, which is available at 1 kilometer, but only twice daily. They combined this with Severi, that's on MSG, which has 30-minute observations, but at a 5 kilometer resolution. And so they combined these two with a Kalman filter and a bias correction to then get daily, or sorry, hourly high resolution 1 kilometer evaporation estimates. And what they did as well is, so this model is using a Priestley-Taylor equation, and they also use surface soil moisture and precipitation to improve their evaporation estimates. And then in the end, they could retrieve, let's say, high resolution temporal and spatially for the whole Mediterranean catchment. They could retrieve evaporation, which could then, of course, be used in the modeling. And so if we're thinking about future, yes, so this is an example of the evaporation. So if we're thinking about the future in remote sensing and also in hydrologic modeling and how Earth observation data can be used, we have a couple of challenges still ahead of us. So as Luca Brocca also said, I agree with him that we're actually only at the start of high resolution Earth observation and modeling in hydrology. So as I mentioned before, some of the challenges that we have is that, let's say, we need more in situ observations to be able to validate and evaluate our Earth observation, but also our model outputs, basically. The other thing that we need is that yes, thanks. So the other thing is also that we can start including novel satellite missions and multi-sensor models. So the upcoming missions are, for example, EcoStress and LSTM and Trishna, which will give us much more information on land surface temperature and vegetation. In terms of microwave observations, we have Roselle and NISAR, which are both L-band missions compared to Sentinel-1, which is a C-band mission. So L-band will give us a deeper penetration depth as well. So we can learn more about more dense vegetated areas. We need to improve retrievals over complex terrain and also include human practices such as irrigation. And last but not least, also improve community practice, sharing data with each other in a fair manner, so that everyone can contribute to these novel data sets and to these models. And with this, I close my presentation. Thanks.
Thank you very much, Mariette. A great way to end this with a very forward-thinking, action-driven agenda. So in the interest of time, I'd like to move over to our discussion panel. And we'd like to explore some of the issues raised by Luca, Lorenzo, and Mariette. So I'm pleased to now welcome our two additional panelists. We have Dr. Giriraj Amarnath of the International Water Management Institute in Sri Lanka and author of the Policy Outlook within the Article Hub. A few words about Giriraj. Prior to his role as a research group leader for water risks and disasters at the IWM, he also worked at the International Center for Integrated Mountain Development. He specializes in the application of remote sensing and geographic information systems in the study of risk assessments across a wide range of natural hazards and monitoring land and water resources in Asia and Africa. Finally, I'm also very pleased to welcome Ilias Pechlivanidis, Associate Professor and Senior Researcher in Hydrology and Water Resources at the Swedish Meteorological and Hydrological Institute. He's also the Project Manager of the Analytics and Dissemination Center for Copernicus Emergency Management Service. He's a member of the World Meteorological Organization, a co-chair of the Hydrological Ensemble Prediction Experiment, and also the chair of the EGU Hydrological Forecasting Subdivision. In terms of his research, he also looks at hydrometeorological forecasting, environmental change impacts, an avid fan of science communication, looking at cross-cutting applications of Earth observations and early warning and user-tailored water and climate services. So that was a bit of a mouthful. So what I'd like to do now is we'll be taking a few of the audience questions. I see that some of your answers are your questions are being answered already in the Q&A. But let's start off with a couple of questions to our guest panelists. So we're all here, fantastic. So warm welcome, Giriraj. My question to you is, in your policy outlook, you state that society should engage with research on the benefits of digital twin technology at this early stage, despite challenges that were explored, such as data availability, model complexity, its cost, also the ethical considerations related to data privacy and access. So in light of what we've heard today, could you please elaborate on the specific benefits you foresee that make early engagement worthwhile, even in the face of all these obstacles such as data availability, model complexity, and cost?
Thank you, Gilbert, and what an excellent presentation from all the three speakers and Frontiers for organizing this amazing forum. Yeah, specifically, if I briefly summarize from the policy outlook that I wrote along with the series of scientific publication that was produced, I think I speak of, we need to have more early engagement on the research we do on digital twin technology, because it is a lot of potential myth to understand across all levels, from policymakers to research institutions and as well as the community. While it holds a lot of potential opportunities, while the speakers have spoken in terms of the whole hydrological water cycle and the narrative of how technologies can be useful for risk management, water resource planning, etc. I think the five areas that we would need to look more closely is on the data governance. A lot of people in the questions have spoken about Global South do not have a lot of consistent data. There is a lack of ownership, and also the expensive nature of coordinating across with the partners in terms of Met agency, technologies, satellite data. A lot of limitations are there, but it provides a lot of promising approach in terms of standardizing, bringing more collaboration between the institution. That's where the digital twin, in fact, at the International Water Management Institute, my colleagues are working already for a Limpopo Basin. And we see already there are fragmentation. The facilitations are very critical at the early stage of the digital twin, hosting and understanding that entire process. But I would also highlight a couple of points specifically. If I look at the disaster risk management is a very critical area that digital twin can play a big role, because it can offer scenario planning like Luca was talking about. You just put some precipitation and look at where the flooding is going to happen and what infrastructure is going to be damaged and what kind of population would be exposed. You could bring a lot of perceptions and also the simulations for mega disasters like flood, earthquake, cyclones, etc. While we have seen just this part of the year, a lot of disasters are already begin, and we do not have a lot of data. So we need to bring more computation skills, and also using the power of machine learning and AI. That's where the ethical consideration has to be even more limited, and that's where the whole efforts have to go. My last summary also is, we need to invest in digital twin technology, because it's going to be more cost effective, because we are harmonizing model development and also improving the efficiency of the real-time scenarios that the policymakers are interested in, particularly in the developing countries. So I'll stop here, but more to add when we go on to the additional question. Over to you, Gilbert.
Thank you very much. I'd like to open it. Would any of the other panelists here would like to say anything based on what Giriraj just mentioned? No. So I think the power of machine learning is definitely one of the areas for data governance we should be very careful with in terms of ethical considerations, but it's very important for us to push forward. And actually, I wanted to kind of pick up on what you said about areas in the Global South also having access and being able to use this in their climate mitigation strategy. So we're going to potentially explore that a bit further on later. So Ilias, I'd like to bring you into the discussion. And what I'd like to ask you is, how do you envision the integration of digital twin Earth technology into your work at the Swedish Meteorological and Hydrological Institute? And how do you think this technology can deliver impact-based hydrological forecasts that are tailored to the needs of different stakeholders, such as policymakers and emergency responders?
Thanks for the question, Gilbert, and good morning, afternoon, evening to all participants. And of course, congratulations to the speakers and authors of this very nice scientific publication. Now, regarding your question, it's good actually to first set the background, saying that the Swedish Meteorological and Hydrological Institute, SMHI in short, provides already state-of-the-art operational services over Sweden, but also over Europe and the globe, with some of our services contributing to, among others, the WMO Green Climate Fund or the Hydro SOS, but also to Copernicus, the Emergency Management Service, and the Climate Change Service. Therefore, there is some experience on that. And of course, there are limitations with this type of services, or better to say, there's space for improvement. For instance, all these nice discussions so far regarding the spatial and temporal information extracted from those traditional hydrological services, hence the added value from Earth observations, their accuracy, and how also the results are visualized, disseminated, and communicated. Now, assuming that these systems are intercomparable, I personally believe on the complementarity of the systems. And this is how I would actually like the integration to be, particularly in river systems that even nowadays they are considered as ungauged or actually poorly gauged, depending on the perspective of monitoring different hydrometeorological fluxes, which is a pity, yet a reality. The complementarity between those systems is actually very important. And although we lack of monitored in situ data, as it was previously said, I think we can find opportunities for relying on the information content extracted from these different type of systems, particularly those providing high resolution data. Now, when it comes to the second part of your question, I believe that impact-based forecasting is actually the future in early warning systems. And why is that? It's because there's effective and actionable decisions need to be made using information on the actual impacts of these hydrological predictions and their extremes. Now, at SMHI, we have our own impact-based forecasting system, and it's actually among the very few national hydromet services with such a product. Yet, as I mentioned before, it comes with its own limitations. Therefore, a high-resolution Earth observation-based service, although it comes with computational cost, maybe uncertainties, and is actually not in real-time mode. However, it comes with specific pros, including the spatial resolution. Therefore, I believe that such services could be used, for example, on demand to provide information at high temporal and spatial resolution and complement the existing products, not only for the national and the regional hydromet services, but also products of the Copernicus Emergency Management Service, and since we spoke about flooding, of the Global Flood Monitoring Service. With such a on-demand services also in near to actual real time, I believe that the policymakers and the emergency responders can have access to products at the resolution that actionable decisions can be made. Back to you, Gilbert.
Thank you. Thank you very much for sharing that, Ilias. Would anyone like to respond or to elaborate on what Ilias just shared there? Well, I think he encapsulated it. Go, over to you, Luca.
Yeah, I simply just want to underline again and to highlight that, yes, I do agree both for the potential of machine learning in all these contexts, as mentioned by Giriraj, and also on the impact-based forecasting. That is something that actually we need to address. And my belief is that now we are close to these targets, much closer than a few years ago. And I see more and more different systems running in this direction. And Ilias mentioned the system that they developed for Sweden, but actually there is also the system for whole Europe and for the globe. And there are also other systems, not too many, but really that's the way to go. And also because some people asked about digital twin and what is digital twin with respect to modeling, that basically seems to be the same things. But the main difference, as I already tried to reply, because there are many questions, and so I try to address some of them. We will not be able probably to address all of them for sure. Is that digital twin wants to make it wants to be something that can be used and interactive with the users. And this is a key challenge because typically only the people running the model are able to use and to understand and to interpret the model. The idea of digital twin is that this modeling system should be available to everybody, and everybody means not only us as scientists, but also stakeholders, citizens, and policymakers. That's the main difference, at least in my understanding so far.
Thank you very much, Luca. Maybe we can use this opportunity to explore the overall concept of the DT hydrology platform. And one question that came up right at the start that I want to address. I've seen that you've done a great job trying to tackle everything in the Q&A. So I've just picked out a couple of them. A question I had from someone called Amin Sadeki, and I guess it would be for you, Luca, is and I paraphrase, as I understand, a water cycle digital twin must include all the key elements of the water cycle, plus real-time or near real-time observations. In the digital twin, how will you consider hydrogeomorphology changes, especially in underwater topography?
Underwater is something that we don't see because it's what is happening below the soil is very difficult to measure and to monitor. And it's one of the main problems in some areas in the world in which groundwater dynamics is very important. It's not very important only for water management. Sometimes it's important also for flooding. And this is something that now we try to address mostly with modeling. Satellite data now can help, but just at very close resolution, which means resolution of 100 by 100 kilometers, but even more. What are doing the European Space Agency and NASA is basically trying to develop a new system with a couple of satellites that can improve particularly temporal resolution of this observation. This is one of the key challenges in terms of what we are able now to observe, both from space and from the ground. And this is something that, of course, we should work on it.
I mean, it's a very ambitious challenge as it stands. So I guess there's more and more parameters that have to be taken into account. Thank you very much, Luca. I'd like to explore a question on data integration, its consistency and uncertainty management. And this is one of the challenges that you flagged in your keynote, Luca. And maybe this would be good. I'd like to ask Lorenzo if you could potentially tackle this one. It's a question from Steven Dietrich, who asked, how could we consider also the importance of in situ observations within the digital twin? Is it only necessary calibration validation for satellite EO and models, or which observations would really be additionally bringing benefit to the suggested twin? I hope you got that.
Yeah, thank you, Gilbert. I'll try to address that. Definitely a challenging question. So in our work, we showed the benefit of state-of-the-art high-resolution. Doesn't mean we don't have to use in situ data whenever this is available. Personally, I think that a combination of all the data that is available after quality check is the best option, meaning satellite data, in situ data, weather radar, or even especially atmospheric reanalysis, such as those provided by the main numerical weather prediction center. What we noted in our modeling is indeed that if you train your model with the same data that you are going to use in operation, that's certainly beneficial. So if you plan to use to a large extent satellite data, then you get higher skills if you also train your model with satellite data. And this is valid for all, so for all data type. So I think that this is definitely key. Of course, further research is welcome by different groups, because it would be very interesting to see if there are any differences by applying this concept to different models, different calibration strategies, especially in view of the application driven by machine learning that are now becoming more and more popular and very skillful. So yeah, I hope I summarized a bit my point. Thank you.
No, I think you did. Thank you very much. Thank you very much, Lorenzo. There are other really, really great questions that are coming out, and I think some of them are taking the data cube into another realm, which I'd like to kind of explore here. Ilias, I'd like to bring you back in and if anyone else is in a good position to answer this, it's great. It's about using this, the data cube for analyzing recuperation of water bodies after these events. So the question is, are you thinking about implementing Earth observation for water quality? This individual here, Emma Garcia, is doing a master's thesis about water quality with hyperspectral image. It'll be interesting to add this type of data in the data cube for analyzing the recuperation of the water bodies after such events. Is this something that could potentially be an application that could be used?
Yeah, thanks, Gilbert, and also thanks for this question. Well, we didn't hear today about water quality that much, because usually we try to focus on the quantity aspects of the different water-related fluxes. But water quality is also very important, even across developed countries. And actually, we have been involved in a couple of projects. They are research projects that they are aiming to monitor some of the water quality, let's say, parameters. And there with CNR, maybe another group of CNR, colleagues have been able to monitor within reservoirs and lakes some of the water quality parameters like water temperature, algae blooms, and so on, and find quite, generate products providing special information about these variables inside the lake. But of course, that was kind of like I think this type of water quality information requires a hybrid approach with process-based hydrological models providing the boundary conditions for some of these hydrodynamic models, including also Earth observations. So if I would have to point to a project, I would ask the participants to check the Prime Water project and another previously funded called SPACEO, but not only those. So technology is there, so potential is also there. Thank you.
Thank you very much, Ilias. Does anyone else want to speak to that? Luca?
Yeah, just want to say that actually the final focus of digital twin is not only the water cycle, and it's not only water quantity. The final target of Destination Earth initiative from European Commission, but also there are some parallel activities in the US and also elsewhere, is to develop a digital twin for the whole Earth, which means water cycle plus energy cycle plus carbon cycle plus biology. I see also some question about that. Biodiversity, ocean, glacier, and so on. As you can understand, it's a very difficult task to address in a single activity, in a single project by even a big consortium. And so currently the solution that we are targeting is basically to make a federate of digital twins. And then the target will be to make them interoperable and to make them speak each other at the end of the day. And so we will be able to try to address not only, for instance, water quantity, but also water quality, but also, for instance, biodiversity, carbon cycle, and all these targets. But it needs time.
Oh, it's a really important direction you can move into, and I can imagine even trying to understand the drivers of biodiversity loss is something that's a challenge within itself. So then finding a way to model that, I can imagine, would be difficult. But it's nice to know that with this basis and this model, we can move forward. So I would want to pivot back to something that Giriraj mentioned at the start, and I wanted to pick up on climate mitigation strategy specifically within the Global South. And this is someone that asked this question. His name is Kent Thomas, and I would understand he's probably from a small island developing states. And his question is, will the resolutions of digital Earth information be high enough that it models small island developing states, as we are historically left out of much of the world's environmental advancement, yet we are some of the most vulnerable? I'm going to leave this open to everyone, but I'd love to hear from maybe Giriraj, if you'd like to share something first.
Yeah, thanks, Gilbert. I think while the modeling environment is looking at downscaling the good presentation from Mariette and Luca was talking about downscaling soil moisture and other. While these capabilities are very good, we do have other series of high resolution satellites are also equally available. During major disasters, you do have potential to acquire, a meter, sub-centimeter satellite images like ISAT. Those are commercially available, but they are equally helpful for, climate risk management strategies to develop. For example, the Open Data Cube, some of you might aware of, and that's also available for a lot of island countries. So Africa Data Cube is also getting developed for, those application and evidences are available, but often awareness and the capacity building to those global south is primarily important to be looked at from my point of view.
Thank you very much. Would anyone else like to speak to that? Mariette, I would like to bring you in if you have any thoughts. More than happy to hear from you.
Yes, no, indeed, with the commercial satellites, there's much higher resolutions that are possible. What is always unfortunate is that they are commercial, so this is a bit of a challenge. Yeah, and in terms of, let's say, publicly available satellites, so indeed, with the Sentinel missions, we're going towards the 10 meters. And I think that what we do here in the digital twin is that we retrieve information for a very large area. So for the full Mediterranean, and even as Luca said before, we're going towards global. And then we are making assumptions, and we're, for example, doing the retrievals at 500 meters instead of staying at the 10 meters to 20 meters that is actually available. If you are working, however, for your own region, you can still use this 10 to 20 meters. It's just a different perspective, right? We need to make a model that works globally, but you can still use, let's say, the Earth observation data and make your own model for your region. What I think is very important there is that we need analysis-ready data, let's say, for the users so that they can more easily use the satellite data. I think currently it's still very hard to use, for example, 10 or 20 meter data from Sentinel. And I think it would be really a big step forward if there is analysis-ready data from the Copernicus missions available to everyone who wants to use it.
Thank you very much, Mariette. That's very, very clear. There's actually something that just popped up that I was going to ask you as well, but it's a less philosophical question. So it's a question about the data you were sharing, and it's from someone called Petrodol, and she would like to know from you, do you include observational data on soil moisture and groundwater storage in your model by data assimilation? What is your source for observational groundwater storage?
I think this is directed to Luca, right? I think.
Oh, perhaps. Yes, maybe. Luca, if you'd like to tackle that one, you're more than welcome to.
Yeah, actually, the modeling, the assimilation part of the modeling was done by Lorenzo and the others. So Lorenzo, I don't know.
Okay, no problem. I can take this. Yes. So in the Digital Twin Earth project, we tested the benefit of Sentinel-derived soil moisture as data simulation. In subsequent work that I briefly showed at the end, we also used data on from trace, so total water storage and the related anomaly, and that was very useful as a comparison with the model. So to adjust that, although it was used as a comparison and for closing the water balance, not as an assimilation. So we're doing a number of experiments also to test that. To give another example, we tried to do a calibration of the model, but by using as a benchmark data not only river discharge, but also satellite-derived soil moisture and evapotranspiration. So what we noted is that you improve the modeling of these additional processes, but you worsen a bit the output in terms of river discharge. So as in, so this is of course a very interesting experiment, and it's good to learn. It was very good to learn. But practically, in our system, operational system, I'm talking, as we mostly aim to forecast floods, in the end, we tend to calibrate, especially on the basis of just river discharges. But this is a very interesting topic, because there is it's like a problem with a large number of degrees of freedom. So depending on which one you touch, you get different results, and it's very interesting, like a very scientific challenge to find the best combination of data to use as benchmark, data to use as input, and what is the best configuration to obtain, let's say, the best system, like the real digital twin of hydrology and the Earth. I think that was my view.
No, that's...
I can simply add that we have used groundwater storage also in the case not only for flood modeling as done by Lorenzo and colleagues, but also for water resource management. And we found it really very interesting to use, but still the resolution is not the ones that we want to, but the potential impact of this data in this topic, so water resource management, is really high.
Thank you. That's great. Looking at the time now, I think we were going to wrap up. So a huge thank you for all the presentations, the panelists. It was really, really riveting to learn from all of your expertise. So what I'd like to do now is to turn to each of you for a few closing remarks about what we've learned today, specifically looking to the critical next steps for this research as you see it. So Luca, I'd like to get kicked off with you as the lead author of the article.
Well, I already put in my slides the key challenges that we wanted to address in the near future, but it doesn't mean that these are all the challenges, because from our discussion, additional challenges are out. And of course, the challenges that I have included in my slides is my own view, of course, in the context of this project. And as we mentioned, a lot of work to be done, but several people and several very nice people is working on that. My only final remarks, because I talked already too much, is that I'm always impressed about the number of people interested in these activities. I'm very happy for that, because it's kind of it merges or integrates all together, many people together, also many expertise. Also my expertise, actually all the activity that I've done in the last 20 years now is going to be concrete in these projects. And so for everybody who wants, because I see that there are 29 questions and we can't answer, and I don't like this kind of things. And so if you have questions, and you can also drop me an email, and with more time, we can try to answer.
Thank you very much, Luca. Yes, I think it was very, very clear what the critical next steps are. Mariette, I'd like to ask you, what are the critical next steps for this research as you see it, and what final thoughts would you like to share?
Yeah, I think what is very exciting is the upcoming missions that are being launched by NASA, ESA, JAXA, Indian Space Agency. So I think with the upcoming satellite missions, we'll have a lot of work to do, and also, let's say, adjusting the algorithms to deal with the different data sets, the different frequencies of the data that we have, but also we can obtain more information about the Earth's surface and get a better understanding of processes using both physical models and machine learning. So a lot of things to do and exciting times to come.
Thank you very much. I'd like to hand over to Lorenzo. What would you like to share?
Thank you, Gilbert. Well, it's been a great opportunity, and I have a lot of food for thought on this. Perhaps I can just list a few challenges for the future. So keeping the pace of the new satellite products that are coming out, and not only trying to use this product in the existing model, but really developing the existing hydrological model or other models to be able to better include this type of new products into the chain, to really have the best output. And also, of course, trying to find the best configuration of the available data, so in situ satellite reanalysis and everything. And then perhaps the last comment would be, as I'm mostly especially involved in the development of operational systems, so that really are used and usable by to save lives and save livelihoods. It's really important that this new product, like satellite product, come out and we work to make it very short latency, so that they can really be used in real time for operational system. This is really important to make it really used and useful. Thank you.
Thank you very much, Lorenzo. And Ilias, I'd like to hand over to you for your words, please.
Yes, with regard to the critical next steps, I think these were well mentioned today, and I just echo their priorities. But I believe that we are actually standing on the brink of a new technology and scientific era, like embracing this transformative potential of Earth observation technologies. And just to say that I'm actually putting my scientific trust in these advancements, including also other advanced methods such as AI and machine learning, to drive the new type of services which are actually going to have impactful and actionable decisions across space and time. Thank you.
Thank you. That was very, very high level and impactful as well. Thank you. And last but not least, Giriraj, what would you like to share with us?
Yeah, so adding to previous speaker, I think to get into these technologies, we also need substantial investment. While digital twin has already shown huge opportunities in urban development, we see already in cities like Singapore, Korea, they are using digital twin in a big way. But when it comes to water science and hydrology, the fundings are very limited. So we need to, while we have seen how technologies have come in a big way, I think there is a huge economic growth. We have also seen how satellite data have shown a huge economic benefit. So similarly, we need to really see how these capabilities can go to last milestone to solve the problems of vulnerable communities, how they can be protected, for which the investments have to go more and more into the developing region, and more case studies are needed to understand the myth of digital twin, and also breaking some of the silos and also bringing greater partnership going forward.
Thank you very much. Those are very clear marching orders. Collective thinking, collaborations, and more funding. I think that goes to speak to quite a few different disciplines where we need to be thinking about planetary health. So with that, I want to thank all of you for joining. It was a really, really engaging discussion today. Thank you to Luca, Lorenzo, Mariette, Giriraj, and Ilias. It was really great to learn from your expertise. I'd like to thank everyone who joined today. I have never seen so many questions come, so great job to the panelists trying to knock them back. I'm sure they'll be flocking to you to ask more questions. But either way, I hope everyone enjoyed the session. So to wrap things up, please do visit the Frontiers in Science website to read the article that we've discussed today. Please also explore the hub of content. You can continue this conversation on social media using the hashtag Frontiers Forum. Please also subscribe to the Frontiers in Science newsletter via the website. The link is being generated and posted in the chat as we speak. And you can visit the Frontiers Forum website to view other upcoming events. A huge thank you, everyone, for joining, all of our guests, and have a wonderful rest of the morning, afternoon, evening, wherever you are, and hope to connect with you all shortly. Thank you very much.